So now Newton's second law, again, we've already talked about briefly, but in short, it just says that the net force acting on an object is its mass times its acceleration. Okay, so in other words, if we have we have some object and we have a bunch of different forces on it. We have force 1 acting on it. Maybe that's colliding with a ball. We have, a second force 2 acting on it. Maybe there's a third force, F3 acting on it, and even a fourth force acting on it. Then the net force, so if we add all those forces together, right, whatever's left, so you can imagine adding these vectors, right? We had F1 like this, and then we would add F2, and then F3 comes back up here, and then we see that that F4 looked like this. So we add all those up. Now we have our net force, and that's equal to the mass times its acceleration. So in other words, the acceleration is going to be in that direction, and this is telling us the direction of it. Okay, and so and like I mentioned, we saw this earlier when we said that the force is the change in momentum with respect to time. And of course, when we looked at interactions like this, we said that that each one of these interactions with some particle was giving us a change in momentum, which was the change in momentum from the first interaction plus the change in momentum change in momentum from the second interaction plus the change in momentum from the third interaction and the change in momentum from the fourth interaction. Okay, and then since force is just the derivative of that with respect to time, right? We just take a time derivative of all of these. So in other words, force, the net force is just F1 plus F2 plus F3 plus F4, which is exactly, what we saw up here. Okay, so we can show it, in terms of equations, and we can also look at it graphically in terms of vectors. And then so now we want to connect these two. We want to connect force as the definition of change in momentum with respect to time as F equals ma. And that's also easy to do because we see that the change in momentum with respect to time is the time derivative of mass times velocity, which is dm dt times v plus m dv dt. So now, in the case of something like a rocket, where you can imagine if you have a rocket that's going up toward to space, and so we have, we're burning jet fuel, then the mass of the rocket is changing, and so we have this extra term in the force because of the changing mass of the rocket. But for the most part, in the interactions we're going to be talking about in this class, that's just going to be zero. For example, if we have two balls colliding, their mass isn't going to be changing. So we just get rid of that term. So we see that the change in momentum with respect to time is m dv dt. But this is just the definition of acceleration. So this is how we can connect force as a change in momentum with respect to time to force is equal to mass times acceleration. So this actually is not the general formula, right? Force as a change in momentum with respect to time is really a more general formula and a more correct way to look at it. Than Newton's second law originally stated. But for the most part, for the interactions that Newton was looking at, and for most of the ones that we're going to do in this class, these two are equivalent because there is no change in mass.